17, first one. And ultimately we have a function here f that is defined as 15 minus g on the interval negative 2 to 2. And ultimately with that we want to know what is the area from negative 2 to 2 of the f function minus the g function. Alright, so ultimately if we were to use what we know, I guess, about our f function here, if we were to replace our f function with 15 minus g, then at least that would put everything within g. If you look at the options that we have there under the list, they all have to do with, they all have an integral with g instead of anything with f. So let's say based on that, our first step should be to replace. So if we do 15 minus g of x minus g of x, and one more. Alright, so with that, if we simplify negative 2 to 2, 15 minus 2g to g of x would be our integral. True? Alright, and ultimately the issue then is can we come up with an antiderivative here? Well, one thing we can do, we could come up with an antiderivative for the 15, but we don't know anything about g here, do we? So with that, if we did 15x on negative 2 to 2, and then minus the integral from negative 2 to 2 of 2 out here, gx here, dx here, and we did a calculation here, we'd get 15 times 2, that's 30, minus negative 30. That would ultimately give us the 60 out in front on some of the answers that we see there. And so at that point we'd be there, we'd have 60 minus 2 times the integral from negative 2 to 2 of g of x dx. And ultimately, I guess that's it, because we can't really do anything with that g, we don't know the antiderivative. But ultimately we could do something with the 15 though, because it's constant, so we could separate that. So ultimately this would be an AB problem, it's properties of integrals. Knowing that we can take our two integrals of a subtraction or addition, and we can separate it, do the integrals separate from one another. And also another property we'd use is we take the 2 out in front, constant multiple. Questions on that one? What else? 16, we have a Taylor series given about the function x equals 3, and ultimately the question is what's the value of f prime at 3, the third derivative of f at x equals 3. Well, remember what those coefficients come from are again that 1, it comes from the fact that it's f of, and keep in mind it's normally f of 0 for us because a lot of ours have been Maclaurin series where it's centered around 0, but instead of f of 0, that 1 is f of 3. And then that 3 in front of the next term comes from f prime at 3. And then the 5 comes from f double prime at 3. And then the 7 comes from f triple prime at 3. So ultimately, what should the answer be then? Since there's a 7 here, we know that in general it's x minus 3 over 3 and then over 3 factorial. All that stuff is there, and what is added to it? The 7 part. And so the 7 part would have to be the third derivative at 3, which ultimately would be letter E. So of course that's a BC problem. Just a Taylor series coefficients, or just definition of Taylor series. What else? 15 through 19. Okay, on 18 we have integral 2 to 4 of d dt of 2t squared plus 2t minus 1 dt. Okay. And ultimately, we could differentiate this if we so chose. And again, it's fairly easy to differentiate here. It's just a power function. But then ultimately, what would we do right after we differentiated that? We'd go right back and anti-differentiate it to get what goes in the box, wouldn't we? For the integral part. So really, isn't this what goes in the box? It's the argument. Okay. Keep in mind when we do it that way, when we differentiate, okay, we get one answer here. And when we anti-differentiate, okay, we get a family of functions here. But ultimately, we can pick which antiderivative we so choose. And so if we choose this one, we would get this. Now, let's say if we just decided to do it the other way, if we just chose to go ahead and differentiate, we'd have 6t plus 2 would be the derivative of that argument. True? And so ultimately, if we were to anti-differentiate, we'd get 3t squared plus 2t, and we wouldn't need a c here because, again, it's a definite integral, so we could choose c to be 0. So bottom line is, are we going to get two different answers then if we use the -1 as our c, or if we use the 0 as our c? Remember, the fundamental theorem states that we can use n antiderivative here when we evaluate this integral. So the question is, again, are we going to get two different answers here then if we choose to use 0 the one way, or if we use the -1 as our c in the other way? Well, let's find out. If we do our 4 in here, we're going to get 16 times 3, that's 48, plus 8, minus 1. Oops. Minus 2 in here is going to give us 12, plus 4, minus 1. And ultimately we're going to get 56, 55, and then 55 minus 15, so it'll be 40. Alright, yeah, so that's that. So if we did that over here on this one, let's see what happened. If we put our 4 in there, we're going to get 48 plus 8 minus 12 plus 4. And we're ultimately going to get 56 minus 16, which is also what? 40. So the question is, why doesn't it matter? And no matter what I have for my c, aren't those two going to subtract each other off every time, no matter what c is? So again, illustrating again that when we anti-differentiate here, when we use the fundamental theorem, part 2, the issue is that we can use any antiderivative we so choose. Right? Because ultimately the c's are just going to cancel each other when we do the subtraction anyway. Right? So either way, we get 40, which corresponds to letter B. Ultimately, again, that would be an AB problem. So just a fundamental theorem of calculus. Part 2. Others? Hey. And let's see, 19. We got 3 sequences of positive numbers, it says. And ultimately, it says if the n approaches 1 to infinity, b of n converges. So that's our given information, the one that we're given. And then keep in mind, the other part of this, right before that, it says that that a of n is between, or a of n is less than b of n, which is less than c of n. So ultimately, the values of the b sequence are between the a and the c sequence. And ultimately, it says which of the following must be true. Well, ultimately, keep in mind that picture-wise, this is like kind of our comparison test, if you will. Here's our b of n, and our a of n would be here, and our c of n would be here. So keep that in mind. So just as a rough drawing, it might look something like that. And keep in mind that if b of n converges, okay, what does that tell us about a of n? Anything below it converges also. So therefore, what could be said about Roman numeral 1? Yeah. Okay, so that one's good. Roman numeral 2 says that number 2 converges. Based on b converging, could we say that c converges? No, absolutely not. So don't know that one. So that one's definitely a no. And then ultimately the next part, number 3, here it says that a plus b converges. So if we have a plus b, well, remember the summation here is like an integral. It's a linear operator here, so ultimately we can just do that and that separated. And ultimately, if we know this one converges and we know this one converges. Keeping in mind if they converge, that means there's a finite sum, right? So if I add two finite sums together, am I going to get yet another finite sum? So what could be said about number 3 then? Yeah. Okay. So therefore it should be 1 and 3 only, which is letter D. So ultimately BC problem, ultimately this is just a comparison test problem. Anything else in that group? Alright, about 20 through 24. 21. 21, we got, says here we have a solid, has a circular base of radius 3. If every plane cross-section perpendicular to the x-axis is an equilateral triangle, we want to find its volume. So ultimately, if we have a cross-section in a plane here that has a circular radius of 3 as the base, keep in mind that picture-wise would look like that. Perpendicular to the x-axis, the slice that we draw, ultimately, and again I can't draw a very good 3D here, but it's going to be a triangle coming out of the page at us, if you will. And what we know about the triangle is that it's what? It says it's equilateral, doesn't it? True? Okay. So bottom line is what we need to figure out is can we write an expression for the area of such a slice? And if we can write that formula for the area of that slice, then we can sum up all the slices by using an integral from, in this case, -3 to 3. Or we could go from 0 to 3 and just double it. It's a symmetric figure here, but either way. So bottom line is, let's see if we can come up with an area formula for that. Now I'm going to draw this in 2 dimensions here, just to keep in mind that if that's an equilateral triangle, the equilateral triangle has to have some nice properties. Number one, if we drop a perpendicular down there, we can get a couple right triangles instead. Keep in mind that that this distance, if this is a circular base, that means the equation we're working with is 9 minus x squared, the square root of. True? And so keep in mind in our picture, let's say that this is the actual base that's on the plane in the cross section. Then ultimately that would be 9 minus x squared, and that would be 9 minus x squared, square root of course. Okay. All right. And which in turn means that 2 minus 9x squared is going to be the entire base, if you will. And would this also be 9 minus x squared? Alright, and keep in mind that with this being a right triangle, and knowing that that's 60 degrees, that's 30 degrees, keep that in mind. Which makes sense with that 30, 60, 90 triangles, because we know that if we know the short side is A, the hypotenuse is always 2A. Okay? And either you can use the Pythagorean theorem here to get this middle side, which we need for the height ultimately. Okay? Or you can recognize that, again, it's a 30, 60, 90, so that means that A times radical 3 is the long side. So, like I said, if you can't remember that, then you'd have to use the Pythagorean theorem. But bottom line here is that height, if you will, in this case is radical 3 times 9 minus x squared radical. Alright, so with that said, we'd have 27 minus 3x squared in here for our height. We don't necessarily need to put that in there. I don't know if that'll do us any good or not. It might be better to just keep it out for the time being, but either way we have 2 expressions that have height here. Alright, so let's see if we can work that out and get something useful here for us. Then it means our area here would be 1/2 times base times height for that particular slice. That's the equilateral triangle. And the base here again is 2 radical 9 minus x squared. And the height is going to be radical 27 minus 3x squared. And we can see that the half and the 2 cancel out there for us. Alright. And ultimately, let's see what happens if we do the math here. Because ultimately the integrand here is going to be difficult if we don't have that square roots in there with those squares, because then we have some issues here. So if we were to multiply these two, we got 27 times 9. And 243. And then it'd be minus 27. Minus 27. And this would be plus 4x squared. Alright. I got that right. Minus 27 minus 27 plus not 4, 3. Duh. That's better. Alright, so with that we got 3x squared minus 54x squared, 3x to the 4th, that is, sorry. And plus 343. Alright, and ultimately, if we factor out our 3 here, we'd have x to the 4th minus 18x squared plus, this divided by 3 would be, that doesn't divide 3, does it? 343. Alright, so much for that. That comes from 9, it's got to be divisible by 3. Or did I, oh, it's 243. Nuts. Let's try that again. 243 divided by 3 then is going to be, what, 81? Alright, now, conveniently here, you'll notice that we have x squared minus 9, x squared minus 9. And so ultimately we'd have x squared minus 9 all squared. Because remember, all that's under the square root. And ultimately the x squared minus 9 part can come out because it's a perfect square. So with all that said, our area formula then simplified would be x squared minus 9 times square root of 3. So that right there would be the area, which is good because ultimately we know we're going to have to integrate here, and if we would have had to have that stuff under radicals here and try to integrate, there wouldn't have been any way to do it. It's not a calculator problem, so it's got to work out nice. Otherwise, there's no way we could integrate that. So keep in mind then if we integrate, bring the radical 3 out in front, we go negative 3 to 3 of x squared minus 9 in here. We get x cubed over 3 minus 9x. Although keeping in mind we have a radical 3 out there. Alright, putting a 3 in would give us 9 minus 27 be negative 18. And then minus, putting a negative 3 in there, we get negative 9 plus, that would be negative 9 plus 27 would be 18. So it would be negative 36, radical 3. And I think I'm missing a minus 9 somewhere because it should be positive, I believe, right? No way, that should be negative. So I got the 36 here. Alright, where are we missing a negative? That part should be good. So again, keep in mind we got the negative 36 in here times radical 3, which gives us negative 36 radical 3. Ought to be a negative somewhere that we missed. Seeing anything I'm missing? That still wouldn't work. Missing negative somewhere. I mean, it wouldn't make sense to be negative here anyway because it's a volume of some sort. You know, in this case, it's a volume instead of area, so it wouldn't make sense to have a negative in there. Well, can't see it right away if we time's sake, we'll move on, and then I'll see if I can find a missing negative somewhere. All right. Anything else on this one? What else? 24. And 22, we got, says the rate of change of the velocity of the particle moving on the x-axis given by the function r of t. Negative sine t minus radical 3 cosine t, time greater than or equal to 0. It says here at the velocity, at time 0, the velocity of the particle is 1. And so the issue is talking about whether we have moving to left or right and speed increasing, decreasing. All right. Now, keep in mind though that this formula they've given us here, and knowing that v of 0 is equal to 1, both of those are important factors, obviously. But this rate of change function here says it's the rate of change of the velocity. True? So if it's the rate of change of the velocity, then really, what is that? And it's acceleration, isn't it? So ultimately, this is actually our a of t function. So if we want to recognize it as such, then ultimately, we want to know something about where the first part here says the particle is moving left or right at time 0. So ultimately, we actually could answer that without even doing any work here, because if you look at the velocity, what's the velocity? The velocity is positive, it's 1. So therefore, it has to be moving to the right, which means A and C are out. True? All right. And then the other part here is talking about whether the speed is increasing or decreasing or constant. Okay? So whether the speed is increasing, decreasing, or constant. And ultimately, that's going to speak to something about the acceleration here. So if we look at our acceleration at 0 is 0 minus radical 3. So ultimately, the acceleration at 0 would be a negative radical 3. True? Okay. So ultimately, what does that tell us? So speed is decreasing, because ultimately, if the acceleration is negative, that means the particle is ultimately slowing down, if you will. Okay. And so therefore, the speed would be decreasing, which would match up with letter D. So ultimately, being AV problems is application of derivatives. Okay, what else? 23, we have a sequence. That's 8 minus n to the 200 over 8 to the n plus 2, and 8 to the n, 3 minus n squared to the 100. And bottom line, it says to what number does the sequence converge as n approaches infinity? In other words, what is the limit as n approaches infinity of this s of n function? Okay. So, knowing what we know about function and behavior, if you look at these two here, this one and this one, okay, those two would be both 200-degree polynomials. And we clearly don't have to multiply that out to figure it out, I hope, because otherwise we'll be spending the whole time on doing that, or more. But ultimately recognize that these are, and the leading coefficients here are just going to be n to the 200 and n to the 200. Okay. Which means that ultimately, what are these going to behave like at infinity? They're going to behave like the leading coefficients, which is 1 over 1, so these two both are really just what? They're 1s. Now, what about these two? Keep in mind, if I have 8 to the n over 8 to the n plus 2, wouldn't that be 8 to the n times 8 to the 2 on the bottom? True? So really, what is this one going to behave like at infinity? 3/4. Does match up with letter D. So I guess sequence-wise, it would seem to be a BC problem here, but really it's more of an algebra problem than anything, isn't it? You really don't need any calculus to do that. But so I guess that it could be on either part. Just sequence evaluation. And ultimately, it's an AB problem in terms of the fact that it's a limit problem, limit at infinity. So I guess I would categorize it as ultimately AB. That could very well be on the AB test. AB student should get it right. What else? There. Anything up to 24 before we carry on to the next part? Ready? 24, they give us the, they want us to find the derivative of the inverse sine of 3x plus 4. So if we have sine inverse of 3x over 4 is our y, and we want to know dy dx, ultimately we need to make sure we know our formulas here for sine inverse. Sine inverse would be 1 over square root of 1 minus the argument squared times the derivative of the argument, which would be 3/4. So it would be 3 and then 4 on the bottom, 1 minus 9x squared over 16 here. Alright, now keep in mind that the simplifying part here, I mean, ultimately you either know that derivative or you don't, basically, and hopefully you do, because that would be good. And then the other part here is making sure that you can do the rest here, which is ultimately, if we were to put these two together, if we got a common denominator for these two, because it's obviously not an option to have that as a fraction with a fraction underneath, then the algebra of that would be, if I were to rewrite this as 16 minus 9x squared over 16, then what could be said about the 16 on the bottom? That could come up. Can that just come out? It's a perfect square. So we'd have 3 here, and then we'd have 16 minus 9x squared here, which nothing can be done with that. And ultimately, what do we have out on the front here? We have 4, but we brought out a 4, but keep in mind the 4 was on the bottom of the fraction of the bottom, if you will. So ultimately, if this 4 comes out, it's going to go here. True? I have 4 over 4, then that equals 1. And therefore, it should be letter C. So ultimately, that would be a AB problem. So sine inverse derivative. And ultimately, the key issue is making sure that you can simplify it. All right, next part, 26. All right. We have integral from 2 to 6 of 1 over x minus 4 dx. And if we were to find the antiderivative of this, keeping in mind that what we need to recognize here is for this particular function is that if I have 1 over x minus 4, that means it's going to be shifted 4 to the right. And ultimately the general shape is this. True? Okay. So the question is, can I find an integral from 2 to 6? Well, so ultimately that's what makes it a BC problem, because it's an improper integral here. We have we'd have to separate this into, we could certainly go from 2 to b, if you will. Find the limit as b approaches 4 from the left of 1 over x minus 4 dx. And we could separate that into that, and then from a to 6, 1 over x minus 4 dx. And we could have the limit as a approaches 4 from the right. So if we set that up into our two separate integrals to see if either one of those would converge or both, hopefully they if they don't, hopefully it's this one, then we don't have to do the other one, right? So antiderivative here would be ln of x minus 4 absolute value of that is. And if we put our b and our 2 in there, we're going to get ln of b minus 4 minus ln of absolute value of negative 2, which of course this is just a natural log of 2 because of the fact that it's an absolute value. And then question is, what about this one? Remember, we're taking the limit here as x approaches 4 from the left. So as we get closer to 4 with our b here, and as we get closer to 4, we're ultimately getting the natural log of 0. True? And if we get the natural log of 0, then ultimately isn't that divergent? So if that part's divergent, then does it really matter what this part does? So therefore it should be letter E. That's correct. So this part right here would diverge, ultimately because it's ln of 0. So again, it's a BC topic, improper integral. Alright, what else? And 27, we have slope field. And it says the slope field for the differential equation is shown below for values negative 4 to 4, and same in the y direction. And ultimately it says which of the following statements is true for all possible solutions of the differential equation. So we can see the general shape, and ultimately the Roman numeral 1 says for x less than 0, all solution functions are decreasing. So if we look to the left of the y-axis here, does it appear that those slopes are decreasing? Look like positive slopes to me. Would you agree? So therefore I'd say 1 is out. How about 2? For all x greater than 0, the solution functions are increasing. Okay, once we get past 0, what do we notice about all the little segments? They're all positive value, aren't they? So I'd say yeah on that one, based on our slope field here. And then how about 3? All solution functions level off near the y-axis. If you look at the y-axis, what do you notice? They're all horizontal, aren't they? So wouldn't that have to be a yes also then, according to that slope field? And therefore it should be 2 and 3 only, which is letter D. So BC topic, slope fields are BC. Oops. What else? Last part. Okay. 25, we have a differential equation. And it says, what are the horizontal asymptotes of all the solutions of the logistic differential equation? And ultimately, we need to recognize that if it's a logistic differential equation, which is a BC topic, and our dy dx here is y and 8 minus y over 1,000. Alright. And ultimately, again, we're looking for horizontal asymptotes here. And keep in mind that a logistic differential equation has an exponential shape, and then it levels off and has some kind of horizontal asymptote above. Okay, so keep in mind that that's the general shape. So if we look at the values that we could have here with this, and we could try to actually solve this and see what the equation is that it comes from. However, it would involve using partial fractions. So may or may not be doable or time consuming or worthwhile. But bottom line here is if we look at our function and we let our y values here, keep in mind if we were to let the y values grow in this differential equation, let's think about what kind of values we'd get here. And again, we don't know the actual function, so it's not like we can put in x and see what the limit is as x approaches infinity here. and see what that is right there. I'm going to point out to you in your book, just so you might want to write this in your notes right now. Something I want to keep in mind to look over. But there is a general formula for this that one of those parts tells us what the carrying capacity is, and that's what we're after. So once you find in your book, I'll show you. It's on page 343. Put it right here. Take a look at it. We can compare it to ours here. On your page 343, the differential equation for logistic growth is going to be this constant times p. Keep in mind that ours is a y, so y here and y here makes sense for the argument that we have there. All right, and so keep in mind that m there is the carrying capacity. Okay. So knowing that, looking at our equation that we have right here, comparing it to that one, we do have a situation where it's almost like that. But again, what we want to do is we want to be able to put it in this form, because if we can put it in this form, then we can identify the carrying capacity with no trouble at all. Okay. So bottom line is, what's the problem with it? We got to recognize is that this 1,000 right here is the problem. Okay. And so ultimately, if we were to, I guess, get that 1,000 out of there, if you will, then how would that look? If we wanted this just to be y only. If we wanted to have that be y only, we'd have to pull the 1,000th out, wouldn't we? Okay. But if we pulled the 1,000th out, we'd also have to pull that out of the 8 as well. So we'd have 8 over 1,000 here. Keep it as such for the time being. Okay. Actually, no, I lied. That would be the opposite. That would be 8,000. So, because ultimately, if I were to multiply that back in, the 1,000th back in, this would get me back to 8. That would get me back to y over 1,000. So now when we look at it now, how does it compare to the general form? Yeah, we have a k over m. We have a in here. Here's our y. Here's our m minus y, if you will, because again, these are like our p's, if you will. And so the question is, how come these two are different? Well, keep in mind, again, one is m, okay, and one is k over m. And ultimately, all that would do, if we know what m is, which m is always going to be in this position, okay, we could use that m to find out what k is, couldn't we? This isn't necessarily k, and this isn't necessarily m. Okay, this is the ratio of k to m. So if they asked us for k, we could find k too at this point. We don't really care what k is in this problem because we just want the carrying capacity. But bottom line is, if we wanted to, we know that k over m is equal to 1/1000th, and we know that m is equal to 8,000. Then we could find k by doing the cross product. We'd ultimately get 8 for k. Okay, so we could find k if we needed to. We don't really need to in this problem, but ultimately that would do it. But again, key is, and again, you might want to put this in your notes to something to make sure you study this logistic differential equation, because ultimately, if you know the logistic differential equation, then it's a fairly easy problem. It's going to be 8,000 the carrying capacity, and which means that our asymptotes would be at 0 and 8,000, which would be correspond to letter E. Alright, so again, key with that logistic, and if you see one, it's probably going to look like that for the most part, and the key issue is making sure you get this by itself, this y by itself right here. So get that number out of there, whatever it is, and that'll give you the m value, which is ultimately, again, the carrying capacity. Questions on that one?
So the answer was E.
Yeah, it should be.
And why couldn't you just set the, since that's the derivative, why couldn't you just set that to 0 and get the...
Let's see. Well, yeah, I bet you could. Yeah, good point. You could do that too. Yeah, because ultimately, you want to figure out, this ultimately, when you look at the curve as it goes left and right, okay, when it equals 0 is ultimately going to be the number in question. Now again, keep in mind that those are asymptotes, so does it actually ever equal 0? No, but if you do set that equal to 0, it should give you a y value that would give, if you solve that, it's ultimately just going to be 8y minus y squared over 100. It would be quadratic, which would be something to be solvable too. Should give you 8,000 and 0 would be your two solutions. So, yep, that would be a good way too. Good job. What else?